Hi, welcome back. This is Jeff again. We're in our second video exploring the linear algebraic nodal analysis algorithm. This video we're going to get a brief introduction to the electronics learning laboratory kit that I built with some students of mine so that we could really make this modeling activity come to life for you. Let's take a look at inside this box. This is a cheap Target box that I got to hold these activities. Here we see a bunch of different electronic equipment. We're going to use this to create real linear systems problems. We'll start with the fundamental component upon which we're going to build circuit. This is a breadboard. In a future video we'll actually take one of these apart and see how this darn thing works. Pretty cool idea though. This breadboard is where we put electrical components in. In every box I try to have 6 of these, assuming that most students are going to work in small groups as we do this in class. Those are breadboards. Next we have a set of resistors. These resistors are 1 kilo ohm. They have a special color coding that you would see that. We try to cut them up into different sizes so that each student that has a breadboard also has a certain number of resistors. These will be the fundamental components in this portion of the linear systems problem construction. Later, when we do more interesting problems with capacitors and inductors, we'll have more interesting components. But for now, when we're just focusing on linear systems, we stay with resistors. The third set of components that we're going to look at is jumper cables. These jumper cables are colored using the standard electrical engineering color scheme. We'll talk more about that in our introductory workbook. We will use those to connect different components on the breadboard. So far we have breadboards, resistors, and jumper cables. Nothing too spectacular about those. The next component that I want to show you, I am really proud of. This component right here is a DC voltage source that connects to a 9-volt battery. My electrical laboratory kit comes complete with 9-volt batteries because I bought these out of pocket. So what happens here is we take this 9-volt battery, we connect it, and 9 volts runs across the red to the black in that polarity. So if you put the bottom part of a multimeter, the negative lead here and the positive lead there, that would measure 9 volts, which is really, 5 volts. This is a 5-volt DC voltage source connected to a 9-volt battery. This is a DC current source, and I believe this one provides 2.5 milliamps. So what that means is when I connect this 9-volt battery to this current source, the circuit inside of this thing provides a 2.5 milliamp direct current from the white pointing to the black. And that stays constant regardless of the load that I put in. Now, of course, some of you who are a little bit savvy would say, well, yes, for high loads, that probably is not the case. And it is true that there is a range of loads that this stays accurate on. But for the modeling purposes that we're going to focus on, we will stay within that range. I do want to give a shout out to both Chris Sakurada and Hayden Sato, and of course Mike Sassnet. We have a whole engineering team that custom built this for these activities. But prior to working with these guys, I had never seen a DC current source as a real component. And this is a really cool thing. Generally, to get voltage sources like this, you have to get a bench power supply, which can be a little bit expensive and quite dangerous, but these allow us to simulate the introductory functionality of voltage sources using 9-volt batteries. Let me repeat this in a different way. These were custom built just so that the people that are involved with this can get a really high quality modeling activity live in a class to teach linear algebra. We are currently still working on the process of trying to make these available for all folks that might be interested. For now, I'm going to make videos to show how these things work until we can figure out how the production process is going to work and how much interest there is in this. I will say that I paid for these out of pocket. These are about $3.50 to $4 each right now. They were also handmade, so that's not really great, but really exciting to have an entire lab ready to go in the hands of students, literally just in a small box. I should mention the last thing. Oh yeah, I guess I'll show you these. These are just 9-volt batteries, standard sack that I carry around with me. And then there are some tools that are standard in electrical engineering labs. There's a digital multimeter. I think I got this one for 40 bucks. There are some like $10 to $15 versions online. Most schools that have physics and electronics laboratories will have a whole stack of these available to students. I also carry at home when I'm doing this modeling, I just have some tools that make taking out components and putting in components a little easier. I think I got this on Amazon, a Work Pro set. You can take a look if you wanted to find those for yourself. And then for me, I like to have some special clips. We'll talk about how to use these on the multimeter later. So this is just a bag of clips that allows me to connect my multimeter to the actual circuits that we build. That gives us an introduction of the Electronics Learning Laboratory Kit that we're going to use to build circuits. In the next video, we'll discuss more about what's happening with these really cool thing called breadboard. We'll actually take the adhesive back off of these and see how they are electronically connected. We'll use that knowledge to build circuits in future videos. I am so excited to share this, and I can't wait to see you in the next video. See you there.